Yaskawa. You're watching the IEC 61131 Basics series. This is part 2 of UsingIO. Hi, I'm Matt Pelletier, and I'm assuming you just finished the first part of UsingIO, and so I'll pick up where I left off. We'd like to also show you at this point the programming best practice when you use I/O. And this is also the way that you will see the I/O when you use Yaskawa's MPIEC controllers. We would recommend you use generic I/O variables in your global variable list. So rather than just applying addresses to existing variables in the POU local list, it's a better practice to use global variables such as di_00, di_01, and to create those variables in your global list, and then even to go so far as to have a separate program POU where these generally named inputs can interface with global variables that operate the different POUs of the code, and also a separate POU for the anything that's an output to control the hardware outputs in a separate POU. So in this case, we have a variable called sensor. We can update that to be a global variable called gSensor, and we'll have a separate input writing to gSensor and sharing that data into the main POU. And then we can swap out gateOpen with g_gateOpen, make it a global variable, and that global variable in a separate program POU will write to the digital outputs. And we'll see coming up here why that's important, which is outlined in these 3 bullets. And the first reason is so that the POUs can be easily reused with other I/O hardware. If you start putting specific addresses for specific modules into all of your different POUs, it's going to be very difficult to reuse that code in another project, and you're thereby really reducing the benefits of using IEC 61131, which is the modularity of your programming regardless of the hardware that you use. As an example, maybe you'll have an HMI communicating over Modbus into certain memory address range. Well, you wouldn't want to go into every POU and put in the addresses for that particular HMI. If you're going to build, as a machine designer, you're going to build another machine which maybe uses a different HMI, and for hardware reasons has to use a different addressing scheme. Perhaps it's using, instead of Modbus TCP, it's using Ethernet IP. So we can keep the hardware I/O as separate POUs. We'll have a lot of advantages as a programmer, because this way, if there is a hardware change, only 1 or 2 POUs will be affected by any hardware change. And so you can see that the way to do this is to transfer this I/O data through the global variables into the different POUs that use the I/O. And there is no performance detriment to doing this. You don't lose a scan or have a slower execution time. There would be a slightly higher memory usage since you're declaring 2 variables where technically you could only have to use 1, but normally this is not a limitation. So I would like you to take the time now to update this program with these best practices in mind, and you can refer to this page as the checklist. We need to create some global variables, we need to create some global I/O variables, and we need to update the latter program POUs. So again, I recommend that you pause the video and see how much of this you can do without assistance. That is the best way to learn. And then you can resume the video to see my solution here. All right, I will update my program now for the best practice with I/O. I'll start in the main POU, leaving debug mode. Sensor is an input. And so instead of a local var variable sensor, I'm going to use one called g_sensor. And making sure to change this to var global. I'm not going to put an I/O address here. And maybe we didn't say this specifically, but let's have open for business. Maybe there's a door that's open or a switch that the operator will use to say that they're open. That will come from an input. So we need a global variable called gopen for business, g underscore. Keep in mind, this is not updating the existing variable. It's creating a brand new variable and leaving the old one there. And then finally, gate open, g underscore gate open, and var global. So now I've got some global variables to be able to communicate this data out of this POU. And I would like also to open the global variables and create some global I/O variables. We could create them for input 0 through 7 and output 0 through 7, one by one. I'll just do a couple of them here, the ones that I know I'll use immediately. I'll use input 0 and input 1. So insert a variable di underscore 00, which will be a Boolean at address %ix 0.0. Also append here input number 1, di underscore 01, which will be at address %ix 0.1. And then for my output, it will be do underscore 00 at %qx 0.0. So now I have these two input variables and one output variable, and they're in the global variable list. So this way I'll have access to them through any POU, but specifically I want to use them in a single POU only as a best practice. And these POUs will be called I underscore PCSIM for inputs and Q underscore PCSIM for the outputs. So let's make I underscore PCSIM. We'll insert the program. It's a good review from doing this before. We want it to be a ladder diagram and call it I underscore PCSIM. And make another one here called Q underscore PCSIM. And then it's just very simple code here. We'll put for the inputs, I will create a couple networks. The first one will take di0 and write that one over to g underscore sensor, and we'll take di0, di1. You can use the arrow key. This is arrow down, down. There we go. di1 to g underscore open for business. So those are the inputs. And now for the output, I'll click down here and add a network. And this network, double click to open that one. We'll take O0. You can see the IO address when you type these in. And we want to write to the gate open. So it's G gate open. Okay, and then be sure that there's an instance in the task. So we'll put in insert a program instance for the I PC sim and insert a program instance for the Q PC sim. Don't forget to choose the program type. Those two match. Okay. We can now download changes. And let's follow this through here. Go to debug mode. Be sure this all works. Okay, I can use input di0. di0 should come into IPC sim. There it is. Does that work? There's the sensor. Why is di1 turning on? Let's look at the global variables. And I see I have a mistake with di01. I gave it the same address. So let me update that here. ix0.1, and let's update the code now with download changes. Okay, back to debug mode. Let's try it again. We'll look at the inputs here. IPCSim. Okay, so number 1 was open for business. Number 0 is the sensor. So we'll turn that one on. It goes to the sensor. Then it should go here to main. Turns that sensor on. Okay, so that's still working. And then G gate open is read by the QPCSim. And you can see I have another mistake in this one. Just trying to see if you guys are paying attention. These are swapped. It's supposed to be that the global variable drives the output. So we'll do G gate open, driving digital output 0. Sure, many of you already caught that as you saw me demonstrating it before. Let's do download changes. These are the kind of things that happen. All right, close the resource. That's why it is important to follow through what you've done. So now the gate open signal is driving the output. I think I just need a few more clicks on this and the gate will close. So this is the best practice along with some troubleshooting of common problems that we'll find. And now the last topic here under UsingIO has to do with the execution of inputs and outputs within the PLC. And this can have very important consequences if done improperly, especially on fast PLCs and on motion-based PLC where inputs and outputs are being read and written at very high rate, and you can't afford to miss them or be a scan behind. So it's time to examine the execution sequence as relates to inputs and outputs. And we've summarized it here in this box. So step number 1, input variables are read in from the input modules. There's then data in all of the input variables that are used, and that data is fixed, and that data is used as the code, number 2, executes. All of the code in the task will execute. And when it all has executed, step number 3 is to write the output variables into the digital output module. So what does that mean for us? What does that mean for the programmer? And what do we have to do? What that means is that the order of the POU instances in the task may affect the operation of your machine. The task will first, it's not even shown here, reading the inputs and writing the outputs is not even shown as an item in this task. But because we have separated the POU that takes the inputs and writes them to global variables, we should do writing the inputs to global variables first and taking the global variables back to outputs last. Because this task will continue to run over and over and over again, and we need to have the correct order of POU instances in the task for the most efficient operation. So let's go into the task list, and whatever yours looks like, let's try to make it look like the one on the right here, where we take the inputs, we then execute main, then we do the money, POU, and the last step is the outputs. So leave debug mode, and let's look at the task. And it's very easy. All you have to do is click and drag. So I'll click and drag this queue down here to the bottom. Okay, I guess that didn't make it all the way to the bottom. Let's put main up here to above money. And for how mine was laid out, this looks not correct. Inputs, main, money, and outputs. And keep in mind that when you do this, one thing I should point out is some of you may have had the project control dialog open. I strongly recommend that if you have this resource box open, you'll have issues when you try to do anything within the resource. So I like to just close it as a habit. Otherwise, what will happen when you try to move these is, here, I'll try it, is instead of moving it, what it really does is creates a copy. Because you had this resource window open, it's not able to communicate with the PLC and change the order of the task execution. So if you had that, you'll want to close the resource box. Very important, you close the resource box. If you have any of these that are like _1 appended here, that's the copy. And you'll want to close the resource box, and then you can delete them. You can't even delete them if the resource box is open. I'll show that here too. If I have the resource box open, you can't delete. It's like this resource box locks in what's in the task, and you can only add to it, but not take away. So close that resource box, and let's delete anything that shouldn't be there. So when you make these changes, this is a change to the physical execution of the PLC. That's the whole reason we did it. You will need to do a download changes. Okay, let's be sure it still works. You'd have a hard time seeing any difference with this application, but we should still do best practice here. I think I need to reset the whole thing. There we go. Okay, looks like we're working again. And there's one more area we need to look at, which is to look a little deeper into the I/O configuration. It's called the I/O task assignment. I had said back a few slides ago that first input variables are read from the input modules, but that action is tied to a specific task. And right now you're only aware of one task, but in reality there can be many tasks happening in the controller. And one of the tasks that's in a sense invisible is called the default task. And it just so happens that the I/O configuration by default goes to the default task. So to make this 100% correct, let's go to I/O configuration, go to input properties, and choose the task called task. So here you can see our task name. It's a interesting name. It's called task. Later we will add more tasks, but for now we have just this one plus the default task. So in I/O configuration, let's start with the inputs and go to properties. And you can see that there is the task assignment. And we would like it to read these inputs at the beginning of the task. That means that this action of reading these inputs will happen before everything is executed in this task. Okay. And let's go to output. Under the output tab, go to properties, and the same for this one. Let's assign the outputs to the task, meaning that at the end of the execution of the output task will be written all of the outputs, as opposed to writing it at the end of the default task. And as we add more tasks here, you'd be able to change that. And just as a side note here, with the MPIEC controllers, you don't normally change the task assignment here. Instead, you'll change it in an area called hardware configuration, which does not work with the simulator. So you can look at our other quick start videos to see more about that. Download changes, which does save, make, and if possible, will download. Now you will see that sometimes download changes is not possible. If there is ever an error with download changes, it just means that that change is not supported, and just follow what it says, and you'll have to do periodically a standard make and download and warm start. Let's click OK. It says here not supported changes in IO group. Okay, fair enough. So what do? We stop. The make was successful. However, if you'd like to redo it to be sure, you can click make again. Okay, so make compiled the code with 0 errors. Now, as we did for the very first download, we'll do again now. You go to download, full download. and a warm start. Close the resource, back into debug. I think we'll see that we can open for business and start sensing cars here again. So let's finish this section with a summary of all of the execution timing by means of this timeline. In reality, we have two tasks going on. One of them we're calling the application task, labeled task here. And then there's the default, the background task, which takes care of other items that the PLC has to take care of. And the first item of business that the task does is to read the inputs into all of those variables with %IB before the task execution even starts. So that's indicated by this green slice here. We're reading in the inputs from the modules into the %IB variables. Then, in order from top to bottom, each of the POU instances will be executed. Each of those takes some time. It may not be a lot of time, especially with our very simple program, but there's some time taken. The last one now, since we've done it correctly, is QPCSim. That was the task that takes global variables and writes them to physical outputs. And then, because of our I/O configuration, the outputs will be immediately written at the end of this last task, written into the modules. Once the task is done, the processor can go to the background task and take care of it. So this is what's happening over and over and over and over again. This is how PLC works. And this is how inputs and outputs relate and are configured to operate in this task. And so I hope with this diagram it makes more sense why we wouldn't want to write those global variables at the very beginning, because they would in that case be written from whatever the result was of the code in the previous scan of this application task. So to keep everything running fast, it's important to think about this and follow some of these rules that we've given. Even though it may seem like extra work in the beginning, it will definitely help in your successful implementation of I/O using IEC 61131.